Good day. For those of you who don't know me, my name is Douglas Harder, and in this topic, we're going to look at some special linear maps and linear operators. So in this topic, we will define a number of special linear maps and operators we will use in this course, including the zero map, the identity operator, diagonal maps, superdiagonal, subdiagonal, and tridiagonal maps. We will also introduce the delay and advance operators for discrete time signals. Now, the zero map, mapping any vector space U to a vector space V, simply maps every vector in the vector space U onto the zero vector of V. Theorem: the zero map is linear. Proof: well, if we apply the zero map to this linear combination of vectors in U, well, it's still a vector in U, so the output is the zero vector. On the other hand, if we calculate the linear combination of the zero map applied to each of those vectors, we get, once again, the zero vector. So these are equal, and therefore the map is linear. Now, the zero map that takes the vector space f to the n to f to the m is represented by an m by n matrix of all zeros and is often denoted with a 0 with subscripted m, n. The identity operator maps a vector space onto itself where each vector is mapped onto itself. So once again, the identity operator is linear. Proof: well, here is a linear combination of vectors in the vector space U, and the identity map maps it to itself. If we take that same linear combination of the identity operator applied to each of the vectors, we get exactly the same result. And so consequently, these are equal, and thus the operator is linear. The identity operator mapping a vector space f to the n to itself is represented by an n by n matrix of all zeros except for all ones on the diagonal, and is often denoted as I subscripted with n. So for example, here we see the identity operator mapping R2 onto R2 or C2 onto C2, and the identity operator that maps f to the 4 onto f to the 4. Now note that the columns of the identity operator are the n canonical basis vectors of f to the n. Now, any m by n matrix with zeros everywhere except perhaps on the diagonal is called a diagonal map or diagonal operator. Generally, we will only use diagonal operators. So basically, here we have a diagonal operator mapping R4 to the R4. And the diagonal entries are lambda 1 through lambda 4. Well, this simply has the effect of multiplying the first entry of U by lambda 1, the second entry by lambda 2, the third by lambda 3, and the last by lambda 4. Any m by n matrix with zeros everywhere except perhaps on the superdiagonal is of course called a superdiagonal matrix or superdiagonal operator. So here we see a superdiagonal matrix mapping R4 onto R4, and we note that the effect of this matrix is to simply shift the values up by 1 within the matrix, setting the last entry to 0, and then multiplying each of the entries by the corresponding value. Note that if all the superdiagonal entries are 1, this has the effect of shifting the entries of u up by 1. Again, also, if an m by n matrix has zeros everywhere except perhaps on the subdiagonal, then it's called a subdiagonal map or operator. As you can see here, this has the effect of shifting all the entries of u down by 1 and multiplying each of those entries by the corresponding value. If all of the subdiagonal entries are 1, this essentially has the effect of shifting all the entries of u down by 1 entry. Finally, a tridiagonal map or tridiagonal operator has entries zeros everywhere except for on the diagonal, subdiagonal, and superdiagonal. So here's one such example, and you can see the result of multiplying a vector u by this particular matrix. Now, as for the vector space of discrete time signals, two common operators are the delay operator and the advance operator. So, if x is the signal where x0 was sampled at time t0, x1 was sampled at time t1, and so on and so forth, then the action of the delay operator is as follows. The delay operator is that signal where each reading is delayed by one time period into the future. Similarly, the action of the advance operator is to now have the reading at time t1 in the location for the initial reading at time t0. So we are advancing the signal in time. So now we start with this the actual signal value at time t1, then t2, then t3, and so on and so forth. So following this topic, you are now aware of some of the more common linear maps and operators, including the zero map, the identity operator, diagonal operators and maps, super, sub, and tridiagonal operators and maps, and as well you are aware of the delay and advance operators for discrete time signals. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!